This session is about forces, which is in paper 2. First of all, we need to know what a scalar and a vector is. Scalar quantities have size or magnitude only, whereas vector quantities have magnitude and direction. So are these quantities scalar or vector? Try and put them in the table. We've got mass, displacement, speed, acceleration, momentum, weight, velocity, distance, and energy and power. See if you can put them in the right places before the answers come up. Mass is scalar. Displacement is vector. Speed is scalar. Acceleration is vector. Momentum is a vector. Weight is a vector. Velocity is a vector. Distance is scalar. Energy is scalar. And power is scalar. A force is a push or a pull that acts on another object, and they can be contact or non-contact forces. A contact force is where the objects are physically touching. Non-contact forces are where they're physically separated, so not touching. So are these forces contact or non-contact? Friction, air resistance, gravity, electrostatic, tension, normal contact, and magnetic. See if you can decide which column of the table they should be in. Friction is a contact force. Air resistance is also a contact force. Gravity is a non-contact force. Electrostatic is a non-contact force. Tension is a contact force. Normal contact is a contact force, and magnetic is a non-contact force. Weight is the force acting on an object because of gravity, and we need to learn the equation for this, that weight is equal to mass times gravity. Weight is measured in newtons, mass is measured in kilograms, and gravitational field strength is in newtons per kilogram. We need to be able to add up forces and get the resultant force, which is a single force that can replace the original forces and have the same effect. If it's in a straight line, it's quite easy. If they're acting in the same way, you just add them up. And if they're acting in opposite directions, you just take them away from each other. See if you can try these ones. 10 newtons and 10 newtons acting in the same direction. These will just add up. So you get 20 newtons. 10 newtons and 10 newtons, again, acting in the same direction, but the opposite direction, will again just add up. But this time the force will be to the left. But in the bottom one you have 10 newtons and 10 newtons acting in opposite directions. These are balanced forces and will cancel each other out. So you get 0 newtons. We need to be able to split forces up as well. A single force can be resolved into two components acting at right angles to each other. They have the same effect as that original single force. So for example, this force can be made up of a horizontal force like this and a vertical force like this. And overall, this will have the same effect as the original force. Vector diagrams are scale diagrams that can be used to resolve forces or to show equilibrium situations or to determine the resultant of two forces. It's got to be done by scale diagram. So in the top right are two forces, 3 newtons and 4 newtons, which are acting at right angles to each other. In this case, we complete the rectangle and the resultant force is the diagonal across it, in this case 5 newtons. we'd have to make sure we drew it to scale. In the second diagram, the two forces are not at right angles to each other, and in this case we get a parallelogram, but it works exactly the same way. Work done is equal to the energy transferred. Work is done when energy is transferred from one form to another, or when a force moves an object through a distance in the direction of the force. So we have an equation. Work done equals force times distance moved in the direction of the force. Work, or energy transferred, is measured in joules. Force is measured in newtons, and the distance moved is measured in meters. 1 joule of work is the work done when a force of 1 newton moves an object through 1 meter. We looked at stretching springs, and this is one of the required practicals that you need to be aware of. When a spring is stretched, the force is directly proportional to the extension, up to the elastic limit. But you need to know how to measure the extension. When we did this experiment, we got this graph of Hooke's law. Up to the elastic limit, the force is directly proportional to the extension. And this end of the straight line part is also called the limit of proportionality. You need to find it on the graph by putting a ruler on the graph and seeing where the line curves away from it. Below the elastic limit, the spring is elastic and it will return to its original length when the force is removed. But above the elastic limit, the spring is permanently deformed and will not return to its original length. It's said to be plastic. You need to learn the equation for Hooke's law. Up to the elastic limit of a spring, the force is equal to the spring constant times the extension. F equals Ke. F is the force measured in newtons, K is the spring constant in newtons per meter, and E is the extension measured in meters or centimeters. You can use the same equation when the spring is compressed, but in this case E would be the compression instead of the extension. We can also calculate out the energy stored in a spring. The equation is half the spring constant times the extension squared. E equals half Ke squared, where E with a little e after it is the elastic potential energy measured in joules, little e is the extension measured in meters, and K is the spring constant measured in newtons per meter. This equation is on the sheet, so you don't need to learn it.